So the next device we will talk are the MOSFET. So MOSFET is short for metal oxide semiconductor field effect transistor. So it is a transistor, as you remembered from last year. So they are, actually four different types. So N-channel enhancement type or depletion type, and P-channel enhancement type and the depletion types. And usually N-channel enhancements MOSFETs are the most common transistors, but it is possible to see the other devices. So if you look at the internal structure, so what you have is you have the gate terminal here, and you have NPN. This is N-type, so this is an NPN structure MOSFET, and you have the source and the drain terminals, and between the gate terminal and the P junction you have a metal oxide layer. So that is where the metal oxide term comes from, and different to VJTs and that kind of things, it is not controlled directly with the gate current, but you just apply a field, a voltage to here, and the magnetic field, the electric field in that one actually controls your transistor. So it is different to a thyristor. It is not a gate controlled device, current controlled, but it is a voltage controlled. But of course, as we will discuss in the next slides, there is a capacitance between the gate and the main body, so you need to charge those or discharge those capacitances to control the device. Okay, so if you look at the VI characteristics here, you see the VDS voltage, and this is the current, ID current, and actually as you increase the VGS voltage, the current goes in that one. So there's also like the linear region, which the MOSFET behaves like a resistances, and in power electronics there are some electronic loads, which are MOSFETs run in the linear region. Most of the time we are using the MOSFETs in the saturation region, and we are just using it on switch, okay, to turn on or turn off our current. We will discuss more on MOSFETs on the DC-DC converters through the semester. And another important thing for the MOSFETs is the body diode. Okay, so for an N-channel MOSFET, the normal schematic is like that, and there's a diode here. This is not a diode that we connect externally. Okay, there's a diode, due to the structure of the MOSFET, and that one is called the body diode or intrinsic diode. So it is just coming from the PN junction of the body and drain and source, and actually I advise you to have a look at that document as well. Anyway, because of the body diode, even if you don't apply any gate signal, okay, whenever there's a positive bias through the source and drain in that one, or if it is a P-channel MOSFET, it's vice versa. But whenever you have positive voltage here, even if you don't apply gate signal, you will have some current flowing through that one. Most of the time, we require that kind of diodes anyway, as we will discuss in the next topologies, because of the inductive loads, and you cannot cut off the current of those inductive components immediately, which will cause quite large voltage peaks. Due to that body diode, actually there's a path for freewheeling the current, but if you are really going at really high frequencies, that body diode is not fast enough. So if you want to increase the efficiency, or if you want to increase the operating frequency, sometimes you add an external fast diode to make that freewheeling effect. Okay. Anyway, so again we will have a look at for the data sheets, and probably you will need to choose one MOSFETs for your hardware project if you are going to implement it using a DC-DC converter topology. There are like different capacitances, and we have gate to source capacitance CGS, and we have gate to drain capacitances and drain source capacitances. So these are most of the capacitances, and usually the most important one is that one, because in order to turn on or off the transistor, there is some current needs to be passed, and your MOSFET driver, the electronic circuit that controls the MOSFET, needs to give that current. Okay, so you can maybe add some series gate resistances, and depending on that resistance value and depending on that capacitance value, it controls how fast you turn on your MOSFET, or how quickly you turn off your MOSFET. I mean, using a faster transition means you will have less losses. Remember, I mean, the idea is you can have the voltage, so voltage can come to 0, and let's say the current, I don't know, we can go like that. Again, it's not as simple as that one, but just for the discussion. So you will have some transition time, and if you multiply the power and multiply the voltage and current, so you will have the switching loss. Okay, so usually reducing that turn on or turn off time will have positive effect to reduce your switching losses. However, on the other side, if you have, let's say this is current, so here you have di over dt's, and having a sharp increase at the current usually results in, if you have either inductive components or parasitic inductances, having a high di over dt means you will have high induced voltages in that inductive loads or parasitic components, so it can create some EMI problems or in some voltage inducing problems, and you will see those effects in your hardware implementation of your projects. Okay, so let's have a look at the couple of MOSFETs. So again, there are like different companies with different datasheet numbers, so on. But anyway, if you look at that one, so we have like 60 volt, 50 amps, and 100 volts. So these are all 100 volts, but the current is increasing, and R on is the on state resistance. So if you have carrying some current, so during the on stage you can calculate the conduction losses by I square R calculations. Anyway, as you can see here, as the current rating increases, the on resistance gets smaller and smaller, because basically they are making the wafers bigger to carry more current, and it has the same effect as like connecting two MOSFETs in parallel, which can be thought as like connecting two resistances in parallel. So it has a positive effect on the on resistance. So again the current will increase, and it is increasing with the square, so you will have more power dissipation, but in the overall it will make you to, for the same current, choosing a larger MOSFET will help you to reduce your conduction losses. However, if you look at the gate charges, okay, this is the charge required to send into the gate to turn on or turn off your device. So for the small MOSFET it was like 8.3 nanocoulombs, and it can go up to 171 nanocoulombs. So that means if you just use the same driver circuit, it will take longer for that transistor to turn on, or if you want to shorten the transition time, you need to use a gate driver which can supply a larger current. Okay, so these are most of the time the on resistance and turn on times actually gives you the main characteristics. This shows how quickly a MOSFET can be controlled, and this shows how the conduction losses changes. Anyway, so for MOSFET, it is a fast device, so it is usually 10 to 100 kilohertz operating range, so it is much faster than Transistor, and it is easy to drive. Okay, it is easy to drive, and blocking voltages, that is a disadvantage. Blocking voltages around smaller than 500 volts. There are a couple of higher grade MOSFETs, but they are more expensive. So because of that, it is not suitable for high power, high voltage, high current applications. And there's a positive temperature coefficient. Positive temperature coefficient means if you have two MOSFETs, okay, if you have two MOSFETs connected in parallel, so the resistance increases with temperature. Okay, increases with temperature. So for example, if you are giving 100 amps, and you cannot make sure they share the current equally. So at first, I don't know, maybe they have 40 amps and 60 amps of the same MOSFET, and because of that one, so that temperature will rise, and that temperature will increase the turn-on resistance, so it will put some pressure to reduce that current, and that will have increase its own current. So there's a feedback mechanism, so it is usually easy to connect two MOSFETs in parallel in order to get a higher power rating. And depending on your application, instead of using a single high power capacitor MOSFET, if you have two or maybe several MOSFETs in parallel, it is usually easier to cool them, because you are increasing your surface area, and it will be easier to dissipate that energy with that parallel MOSFETs. And again, you have the body diode. So body diode can conduct the full rated current usually, and it will help you for the freewheeling application. Okay, but usually that diode is kind of slow. So if you are working at higher frequencies, even if there is the body diode, it can be you can connect an external diode, so it will be faster and more efficient than the body diode. Okay, so switching time is determined by charging and discharging gate capacitors. So you have the CGS, and there is charge needs to be given. So depending on how much gate current is your driver giving, so you can change the turn on or turn off time. But again, it is quite a fast device, so it will be applied for tens to hundreds of kilohertz for switching frequencies. So let's move on to our next device. It is IGBT. So that is also quite common for power applications, because it has a higher voltage rating than MOSFET, and it is short for insulated gate bipolar transistor. Okay, insulated gate bipolar transistor, and they are usually sold with like modules like that. So they have not a single IGBT, but depending on the topology, you have 3 packs, so 3 IGBTs in a single package, or 6 packs. Probably those are the 6 packs IGBTs, and you can have like the full 3-phase full bridge application, like in the 6 diodes we already discussed. You can have the 6 IGBTs, and those large terminals are for power, and small terminals like that one, or small terminals here, they are usually for gate signals, or in some cases you have some self-protection circuits inside those modules, so it can give you an error if temperature is gone above the limits, or if the current is too high, etc. Okay, so IGBT is basically a hybrid transistor. So it is like a BJT. Okay, for the power stage it is like a BJT, but instead of like getting all the current through the base, and like this is like more like analog system if you remember it from third year. So it is combining MOSFET and BJT, so the gate is similar to MOSFET, but that structure, you know, is basically like a BJT, so it's basically that term coming from, and it can be used for like really high voltage and current applications, and for voltage ratings like, let's say, above 500 volts, like MOSFET is not suitable. So IGBTs can withstand those voltages. They are like 3000 3000 volts IGBTs, like in several hundred amps. Okay, and they are not as fast as MOSFETs, but they are quite fast. Again, you can have switching operation depending on your voltage and current rating, like tens of kilohertz are usually applied. So it is, you know, slower compared to MOSFET. It has lower on resistance. That is important, especially for high currents, because you have I square R losses, and they have, it is not like you have constant R on resistance, but there's a forward voltage, and depending on forward voltage you can calculate the conduction losses. Again, you know, it can withstand higher voltages. I think there are even some modules higher than that one. And at first it was quite difficult to parallel IGBTs, because they don't have that kind of distinct positive temperature coefficient like MOSFETs, but the newer generations have that possibility. Okay, so if you are working for motor drives or that kind of things in the power applications in the kilowatts range, megawatt range, and if your voltage is within like 500 volts to 2000 volts, then probably IGBT is, you know, is the most common and the most suitable device that you can use. And again, here you see like different devices. So this is a 600 volt device and 32 amps. The other one is 1200 volts. You know, the power rating is more or less same, but again we have a similar trend like as in the diode. Higher rated voltage usually means as a higher voltage drop. So this is forward voltage, so the conduction losses will be directly like that. Again, this is the transients, and it is not as fast as MOSFET. Again, you have like that one. I think, for example, I think they managed to find a way to find a lower forward voltage. And we will see those devices throughout the semester, and I will also show you a data sheet in the next slides. Okay, so let's see that data sheet. So we have 1200 volts, 40 amps high speed data sheet device. So okay, now we have our IGBT. Again, let's have a quick look at those features. Again, this is a higher temperature device, 175 Celsius. They say high speed switching series. We will talk about that tail current. And normally the forward voltage is around 2.1 volts. I mean, whenever you see typical, probably it is the best value, and we will see the detailed explanations in the data sheet at 40 amps. Okay, so it can withstand a short circuit of 5 microseconds. You know, we will see the current limits. So safe paralleling, so probably it has a positive temperature coefficient, so it is safe to parallel. So you can connect a couple of those things in parallel, and they can share the current. Very fast recovery anti-parallel diode. So they have this diode, okay, and it is not the body diode, so it's, I think, in the package there's another fast diode, and there's a low thermal resistance. Low thermal resistance means it will be easy to dissipate that heat. Okay, and again, applications like UPS, welding machines, photovoltaic inverters, high frequency converters, blah blah. Okay, so let's have a look at this. It's quite a long data sheet. Again, the voltage rating is around 1200 volts, and continuous current is around 8 amps at 25 Celsius. So it can carry more current if you can keep the temperature low. However, if the case temperature, C is for case, if case temperature is increasing up to 100 Celsius, the current rating will be around 40 amps. Okay, so again, it can withstand pulses for 160 amps, and it will be controlled, gate emitter voltage, it will be controlled with positive minus 12 volts. Okay, and I think that one is the limit, 30 volt is the limit, blah blah, and total power dissipation, and it goes like that. And they have the thermal resistances. We will talk those things in the following weeks. Junction to case for the IGBT diode, so internal diode, and the junction to ambient is like 50 Celsius per watt. Anyway, so again, that number is quite important to calculate the efficiency or conduction losses. So again, in the first page it was given as 2.1 volts, but as you can see here, it is the best voltage. So it is when VG is 15 volts and collector current is 40 amps, then you can have 2.1 to 2.6 volts of forward voltage. However, that voltage goes up. Okay, that voltage goes up as the temperature increases, so it goes from 2.1 volts to 2.4 volts, and at the limit it can reach up to 2.5 volts. I mean, that's quite dangerous, because if you didn't design your thermal system properly, so here it will cause some power, then it will heat up to 125 Celsius, then it will create even more power loss, then it will try to increase the temperature, so there can be a thermal runaway. So there's a feed forward mechanism here. Okay, so what else? Collector cutoff current, microseconds, microamps, and this is the the cutoff current. And gate emitter leakage current, so there's a leakage current of 250 nanoamps. And again, they have the dynamic characteristics for input capacitance, output capacitance, like it's the picofarads. And this is again similar to what we discussed in the MOSFET. There's a total gate charge of 158 nanocoulombs, so your driving circuit will charge that capacitor to turn on or turn off your device. Okay, and again, usually it is, if you are controlling your gate with that kind of parameter, so this is 10 ohm gate resistance, 15 volts, blah blah, and the delay is around like 18 nanoseconds. Current rise time is like 37 nanoseconds. Those are quite fast values, and that one is quite useful data. Some data sheets giving these two. I think they can be directly used for switching losses. There's the turn on switching energy and turn off switching energy. How much energy that it is, again under that current and that voltage. So it is like for turn on it is losing 1 millijoules, and for turn off it is 1.32, and total switching energy is 2.32, so 2.32 millijoules. And let's say if you are working at, I don't know, 10 kilohertz, so you are multiplying, you are doing that thing 10,000 times a second, so power is equal to 23.2 watts. I mean, this is just the switching losses. On top of that, you can have the conducting losses, and you will add these two, and you can, by using the thermal analysis, you can estimate the operating temperature of your device. Okay, and again, they are like different, so this is for a different operating condition. So now I think this is when it is cool, and when it is heated up, similar to conduction losses, the switching loss also increases. Okay, and again, it has a diode, it has a separate diode, and it has the relevant information for the diode as well: reverse recovery time, peak reverse recovery current, so on and so on. So you can see it is again in the order of nanoseconds, so it is a kind of fast device. And again, reverse recovery current, reverse recovery energy is how much energy that you are losing in the diode switching. And if you look at the next characteristics, they are all how the voltages changes with temperature, with currents. So again, those numbers, those figures are just given for specific operating conditions, and it is usually you can start with those numbers to start, but once you have a detailed understanding of device operating points, it will be helpful if you can just find your operating points through those graphs and check if it is within your limits. Okay, and again, if you just go below, okay, so let's have a look at other parameters, and there's like test circuits, there's the switching waveform, so you can actually see what all those definitions are, and this is the diode reverse recovery waveform, and again the package information, the dimensions and that kind of things. Okay, so this is the IGBTs, and actually we can also discuss for some new transistor technologies, apart from the silicon based transistors, there are a couple of newer technologies. So one of them is the GaN transistors, so they are short for gallium nitride. So they are becoming really popular, and they are really efficient and fast switching transistors, and using especially for commercial electronics. So usually it's similar to MOSFET, so they are usually less than 600 volts, and most of the time it's even less than 100 volts. So GaN devices are really fast, so they can minimize the switching losses, and they can go up to megahertz range without no problem. So it can help to reduce your power converters. And actually I advise you to have a look at those links. Okay, so and the other one is the silicon carbide. Okay, that one is also becoming popular, especially in railway traction or electric cars, that kind of systems. I think Tesla now uses silicon carbide inverters, and I think that photo is from Toyota Prius. So the first generation of the Toyota Prius inverter with normal silicon IGBTs are like that, and this is the same power rating, but you can see the size and the mass of the inverter is quite reduced. So that makes your electric car lighter, or you can use that space for other things, or for the same volume or mass you can achieve a higher power ratings. And of course the idea is same, so silicon carbides are faster than IGBTs, so they can go up to higher frequencies, and with higher frequencies it helps you to reduce the size of the passive components, and also switching losses are low. So once you get rid of that thermal burden, so you can make your transistors smaller. Please have a look at those reading materials, and it can give you some insight about the GaN and silicon carbide transistors. And actually, if you look at a comparison here, so we have, this is the voltage levels that we are working on, and this is the performance criteria. Okay, it's not always, there's always the cost, and GaN and silicon carbide are slightly more expensive at the moment. Probably they will become cheaper and cheaper in the next years. But anyway, if you are working at low performance and low voltages, so we can have the normal MOSFETs, silicon MOSFETs, that kind of things. And if you are going to higher voltages, and if the performance is not that important, you have the IGBT transistors. And if you are working at high voltages, and if efficiency and the cost, efficiency is important, but cost is not that an important factor, maybe you can use silicon carbide devices. And again, GaN is mainly used for lower voltages and high performance applications. Okay, and we will discuss the application of those transistors and those technologies along the way. And when you are doing your hardware projects, you can have a look at suitable products if you want to use that way. Okay, so that's all for today, and see you in the next video.